So first of all, I would like to thank the organizers for giving me an opportunity to give this talk on behalf of Jean Bourgain, who unfortunately was unable to come. And it's very nice to be giving a talk in Wrocław, especially in my case, because in fact my PhD advisor, Maciek Zworski, was born and grew up in this city. So let's see, where is the clicker? So what I will talk about today are some applications of harmonic analysis to, one could say, mathematical physics, and more specifically quantum chaos. And the main harmonic analysis tool can be described, well, I personally call it fractal uncertainty principle. So I will state what it is precisely later on, and I will spend most of the talk explaining how it is proved and talking about this genuinely harmonic analysis question. I would like, however, to start with some applications and why interest to this fractal uncertainty principle appeared in the first place. So let me start with an application to non-compact hyperbolic surfaces. Let's say take a convex co-compact hyperbolic surface. So what is it? It's just a complete non-compact Riemannian surface of sectional curvature -1. And you can also view it as a quotient of the hyperbolic disk by of the hyperbolic plane by a group of Fuchsian transformations, which only has hyperbolic elements and a finite-sided fundamental domain of infinite volume. Now, sorry. Thank you. So here is a basic example of a convex co-compact hyperbolic surface. This is maybe the smallest non-trivial example, which is generated by a Schottky group on 2 generators. So on the left, you have this 3-funnel surface. That's if you want to view it from point of view differential geometry. If you want to view it from, view it algebraically, then you can look at its covering space. And then you have a tessellation of fundamental domains, and they are mapped to each other. These cuts are mapped to each other by 2 group elements, which together generate this group gamma. And it turns out that actually any convex co-compact hyperbolic surface can be viewed in this way with more sides to the fundamental domain. All right. So the object that I want to talk about on this hyperbolic surface is our resonances. So historically, they were first defined using the Selberg zeta function. So this is an Euler-type product over lengths of primitive closed geodesics. And then it was proved that this Selberg zeta function has meromorphic extension to the complex plane. So understanding the singularities of this Selberg zeta function, understanding its zeros, it tells us about the behavior, the asymptotic behavior of the length spectrum of your manifold, just like understanding the singularities of the Riemann zeta function tells us about prime numbers. Now, from my point of view, I'm by training a microlocal analyst and you could say a mathematical physicist. So I come from the second way of viewing these zeros. So it turns out that they correspond to what's known as scattering resonances. So if you look at the Laplace-Beltrami operator on your manifold, it has an essential spectrum and absolutely continuous spectrum starting at 1/4. Now, what one can do is one can make a change of variables. There it is. Which is often written this way, really to conform to the previous Selberg zeta function notation. And what this does is that this moves 1/4 to 0, and then it unwraps it. And so what was here, this physical plane, becomes real part of S bigger than 1/2. And then the L2 resolvent here can be viewed as an operator depending on S. What's non-trivial, however, is that this resolvent can be meromorphically continued if you restrict both the domain and the range. If you want its integral kernel can be meromorphically continued to the entire complex plane. And then you could have some singularities here corresponding to small eigenvalues of the Laplacian. But left of this real part of S equals 1/2, you have these new singularities, new poles, and they are called resonances. And so it turns out that these resonances actually tell us about long-time behavior of solutions to the wave equation. So I'm not going to go into detail about that, but that's the reason why these resonances are defined this way in the first place. Now, so it turns out that in constant curvature, these two, the Selberg zeta function singularities and these resonances, are actually related to each other. Now, the specific question that I want to ask here is whether or not a given hyperbolic surface has an essential spectral gap. So what's an essential spectral gap? It's a strip left of this unitarity axis in which there are only finitely many resonances. It would be best, of course, just have no resonances, but that's a separate question. Quite often it turns out that there might be, for example, one resonance on the right and nothing else on the left. So in order to understand whether this spectral gap holds or not, it turns out that it's important to look back at this picture, specifically at the geometry of this tessellation by group actions, by fundamental domains. Namely, if we look at this picture here, imagine that we take the circle and then we remove every infinite end of the fundamental domain. Here, the boundary of the circle, of course, the circle corresponds to the infinity of the hyperbolic space. And then we keep repeating this procedure. So we just remove this infinite ends in each of the fundamental domains. And that's a Cantor-like procedure, which, when repeated, gives you a fractal set. And so this set is called the limit set of the group. And that's a closed subset of the circle. So it turns out that understanding the limit set is crucial to understanding what happens with this spectral gap question. I cannot really go into details why, but very briefly, if you look at solutions to the wave equation, at high frequency, they propagate along geodesics. Now, what the limit set has to do with geodesics is that each geodesic here can be lifted to a geodesic on the hyperbolic plane, and then depending on whether the limits of this geodesic at infinity do or do not lie in the limit set, this geodesic will either be trapped or it will escape. And so the limit set contains information about the trajectories that will escape, that will stay trapped for a long time, and these trajectories can support high frequency waves for a long time, and thus they are the natural abstraction that has to be dealt with if you want to prove wave decay. Now, the limit set has a lot of nice properties, and in particular, one can compute its dimension, which is typically denoted by delta. Turns out to be both Hausdorff and Minkowski dimension of the limit set. It's between 0 and 1, and all interesting cases, so except the hyperbolic plane and hyperbolic cylinders, it's strictly between 0 and 1, so that's the assumption that I'll make. So what was proved by Patterson and Sullivan is that the rightmost resonance actually lies at delta. So I can place it here, or I could place it here, of course, depending on what this number delta is. On the other hand, just from the spectral representation, you can see that you always have finitely many resonances to the right of real part s equals 1/2. And so from these classical results, you can get the following diagram. This is supposed to be a straight line. So this is the gap that you can get from these classical results. And so the question is, can one do better? So in the regime where delta is no more than 1/2, one can actually do better. And that was proved by Noy in 2005, that you actually always have a gap, except in the trivial cases. You always have some gap that's strictly bigger than 1/2 minus delta and depends on the surface. And that's already a rather non-trivial to prove. In fact, it relies on techniques that originated in Dolgopyat's 1998 paper on exponential decay of correlations for and also flows. Now, what I will present today is a result that's interesting when delta is bigger than a half. And so what it says is it says the same kind of statement, namely, you always have a gap, but now you always have a gap strictly bigger than 0. So what it tells you is that the Patterson-Sullivan gap, it only worked under the assumption that delta is less than 1/2. And there is a more general pressure gap, which arises for more general open quantum chaotic systems, which generalizes this one. And then the result of no shows that you also can have a gap when delta is equal to 1/2. What we show is that you always have a gap. So we handle the remaining cases. And so there are multiple applications of this. In particular, one nice application is, as I mentioned, the resonances interpreted as poles of meromorphic continuation of the resolvent have to do with asymptotics of the wave equation. And so a gap like this tells you that you would always have local energy decay for the appropriately defined wave equation on any convex co-compact hyperbolic surface, modular finitely many terms which have to do with these finitely many resonances that were there and, of course, have to be analyzed separately. So this is a model case and an important model case of a more general conjecture that if you have any manifold with reasonable infinite ends and with geodesic flow which is hyperbolic, so you have unstable trapping situations there, then as soon as the manifold is at least a little bit open, so as soon as there is some possibility of escape, you will have exponential decay of linear waves. So that would be a special case of this conjecture for the class of hyperbolic surfaces. All right. So now let me pass to the harmonic analysis part of the talk. So in previous work joined with, I haven't gotten to that part. Right, I have to talk a little bit about the limit set first. So I have to set up some notation before I can introduce the fractal uncertainty principle. So let's remember that we have this limit set, which is a fractal set, and it has a well-defined Hausdorff dimension. In fact, this limit set is much better than something with a Hausdorff dimension less than 1. In fact, you have a rather precise estimate on the Hausdorff delta measure of neighborhoods of points in this set. So that's known as Alford-David regularity. So you have this upper and lower bound, that's the Hausdorff delta measure of an alpha-sized interval centered on the set, intersected with the set, grows like alpha to the power delta. So it means that it has the same dimension at each point at every scale. Now, in order to set up the fractal uncertainty principle, I will have to consider the following operator. If you do hyperbolic geometry, you might recognize this as a version of the scattering operator of the hyperbolic space. So it's actually a natural operator that appears in hyperbolic spaces. If you want to think of it in terms of harmonic analysis, which is probably better here, this is just an integral operator with a highly oscillating kernel. This absolute value y minus y prime is the Euclidean distance. And you cut off from where, you cut off away from the diagonal. So this is really a rapidly oscillating function. You can write it as e to the 2i over h times log of this, and then you really see it's a Fourier integral operator. And it's normalized to be unitary. Well, not exactly unitary, but, for example, being bounded uniformly in h in the L2 space. And so that's a hyperbolic analog of the Fourier transform. All right. So now I can state the fractal uncertainty principle. So what does it say? It says that, well, it's just an operator norm bound on the L2 space of the following sandwich. You put this hyperbolic version of the Fourier transform in the middle. Remember that that had norm about roughly 1. And then you put cutoff function. So you just put multiplication by indicator functions of h neighborhood of this limit set. So here you should think of h, we call it semi-classical parameter, but that's the effective wavelength of the system, and it's the inverse of frequency on which, of oscillations that you study. All right, so that's the statement. So obviously, if you just put the cutoff on one side, your norm would be like 1, but once you cut it off on both sides, it turns out that you get an improvement, and this norm decays like a power of h, and this power is some positive number that depends on the quotient. All right. So, well, this is a statement about a particular integral operator. It turns out that the specific phase we had in our operator doesn't actually matter here. So you can reduce this statement about this operator with this integral kernel by a linearization argument using the Kottler-Stein lemma, so almost orthogonality, to a statement for the usual Fourier transform. And then when you undo the semi-classical rescaling, then you end up with a situation that looks like this. So imagine that you are given two sets. So the only property that we will use about the limit set is its delta regularity. It's a strong property, but we will not use self-similarity or the group structure of the limit set beyond this. Now, let's assume that we are given two delta regular sets. And since we did we undid the semi-classical rescaling, one of these sets, x, it will lie in, say, the interval 0, 1, and it will be delta regular on scales h to 1. And then I'll define n as 1 over h henceforth. The other set y is, let's say, in 0, n or minus nn, and that is delta regular on scales 1 to n. So you should just think of this x as being union of h-sized intervals, which are distributed in a fractal way, so that you have counting estimates on the number of intervals in any intermediate scale piece. And y is similar, but it's a union of size 1 intervals. Now, so what's the Fourier transform statement? Well, you can translate this bound to the following, that if you have any L2 function, and you know that the support of its Fourier transform lies inside y, then restricting it to x and taking the L2 norm will give you a small, just a small piece of the total L2 norm, specifically a negative power of this frequency n. Right? So that's why it can be called an uncertainty principle, because it tells you what would be a counterexample to this. A perfect counterexample, which of course wouldn't exist, would be a function whose support is exactly in y. Sorry, the Fourier support is exactly in y, and the support of the function itself is in x. Of course, that's impossible because if your Fourier transform is compactly supported and you are non-zero, obviously you cannot be compactly supported. But this is a more quantitative statement of this form. So you can only have n to the minus beta power of the L2 norm here. So this is about localization to a fractal set in both position and frequency, or rather leg thereof. So it turns out that for some values of delta, this fractal uncertainty principle isn't hard to prove at all. So I'll leave it as an exercise. I hope the audience doesn't feel insulted by such a simple exercise. But it's really easy to show that you can get this fractal uncertainty principle with beta equals 1/2 minus delta. Just by using the volume of this set. So, which actually recovers exactly this Patterson-Sullivan gap. So it turns out that the simple argument that gives you this basic fractal uncertainty principle, which I call the volume bound because it only depends on the volumes of the sets involved, actually gives you the Patterson-Sullivan gap. Now, if you want to go beyond that, that's an exercise I didn't put in. But if you only allow yourselves to use the volume of the two sets, then you cannot push past this graph, maximum of 1/2 minus delta and 0. For instance, if your delta was equal to 1/2, you can just take a Gaussian, and that will live. It will have a good portion of energy in an interval of size h 1/2 here, and in an interval of size n to the 1/2 there. So in order to push past the standard or the trivial bound here, you really need to start using the structure of the set. You have to use the fact that the set has a lot of holes, if you want, on many scales and many points. All right. So before I go on with the proof of this fractal uncertainty principle, I will, I forgot to mention, so there is an earlier work of Dyatlov-Zal, which shows that this fractal uncertainty principle with exponent beta actually implies an essential spectral gap with exponent beta. So I'm not going to go into the details of that, but that was the original motivation. Another motivation was this application to the compact case, which is a recent work joined with Longjin. In fact, it should be 17, I apologize. So imagine you have a compact hyperbolic surface now. So just maybe I'll draw it here. So compact case. Now, people are split in hyperbolic surfaces. Some of them care about non-compact ones, and some of them don't, but everybody seems to care about the compact case. So here's something on a compact case that you can do using this technology. So just take a compact hyperbolic surface. Take any non-empty open set. Any non-empty open set. Then consider an eigenfunction of the Laplacian. Then the L2 norm of this eigenfunction on this open set is bounded below, assuming, say, it was L2 normalized. And the constant, well, you can certainly bound it below with constant depending on frequency. That's unique continuation principle. But the point here is that the constant actually doesn't depend on the eigenfunction or on the eigenvalue. So this is really a high frequency statement. So this statement is quite useful for applications. So I'll just list one here, that it implies control for Schrödinger equation by any non-empty open set, which is known in very few cases. I think it's actually only known for the torus. At least it was known only for the flat torus before, and to do a completely different reason than here. And you can actually make this statement microlocal, so you can not only restrict to an open set in position, you can also restrict to a cone of frequencies, and you will still have a lower bound. And that implies that any semi-classical defect measure, so any microlocal limit of a high-frequency sequence of eigenfunctions, actually has support which is equal to the entire cosphere bundle. So it has full support. So there is a long history of study of those that I'm not going to get into, but there is a quantum ergodicity theorem which tells you that most eigenfunctions will equidistribute in position and frequency. And there is a quantum unique ergodicity conjecture of Rudnick and Sarnek that states that the whole sequence of eigenfunctions should equidistribute. And so this is some middle ground. Well, certainly farther from quantum unique ergodicity that one would hope, but still it tells you some restriction on what limits of high-frequency sequences of eigenfunctions are possible and what are not. All right. So, all right, well, let me move on to actually proving fractal uncertainty principles. So the rest of the talk will be harmonic analysis. So how do you prove a statement like that? So let me erase this. Well, so here you just need a tiny improvement, right? As far as powers go, I'm not promising a big beta here. There is some work in progress to compute what beta actually is, depending on delta and regularity constant. It's excruciatingly small. It can be extracted, but it's rather small. But what are we improving over? Here we're improving over the statement, that the Fourier transform is unitary, if you want. Here we're just improving over the total L2 norm. So in order to get an upper bound on the total L2 norm in a smaller set, one can argue it's enough to have a lower bound on the complement. So roughly speaking, if you look at this set X, you can see that this set X, because delta is strictly less than 1, so the dimension is strictly less than 1, it has a porosity property. So it has holes at all levels. So no matter which interval you take here, you will be able to find a subinterval of a fixed relative size so that it doesn't intersect the set. So the idea is to use an iterative argument And think of the set X as progressively removing smaller and smaller intervals, but more and more of them out of the set, and taking, and estimating from below how much of the L2 mass was removed on each time, using, of course, the restriction on the Fourier support. So I will just state the first step of this, which is called here a main lemma. And it turns out that the other steps are not very hard to obtain from this one, using the fact that this Fourier fractal uncertainty principle is scale invariant. So it actually scales correctly, and once you prove this, you can really iterate it and get the full statement. So what do we need to do? So let's see. Do I have it somewhere? Maybe I should. OK, that worked. So from now on, we'll consider the following situation. So I'll forget about the set X. So I just discretize my set X on a certain scale. And then what happens here is that imagine that you just look at partition of R into the usual unit-sized intervals. And imagine that inside of each of these intervals, which are called I, you choose a subinterval of fixed size, which I call I prime. So there are lots of I primes. For each I, you choose this I prime arbitrarily. How are these I primes chosen? They're chosen from the set X. They are the holes that are missing from X. So what you want to show is that if you have the Fourier support property, so support of f hat is inside of a delta regular set Y, then you have a lower bound on f on the union of all of these intervals. So that's what you really need to show to get these improvements. Wait, did I start? I started 10:30, not 10, right? Yeah. OK. It's, I lose track of time when I start talking. All right, so, so how do you show this? Well, once we reduce this upper bounds to lower bounds, we are really in a territory of quasi-analytic classes. So we want to, this is like an effective uniform continuation principle for a function. The only problem is that the usual theory of quasi-analytic classes asks the following question. How fast should the Fourier transform of a function decay so that you cannot have, say, compactly supported functions, or you would have lower bounds and intervals? And here we do not have a rate of decay on the Fourier transform. Instead, we have a support property. So the difficulty here comes in how to use this support property and then combine it with known results in this rather rich and well-developed field of quasi-analytic functions. So, well, the first step is the following bound, that if you had a function with compact Fourier support, then, well, it's real analytic, so you expect you should have a lower bound on any interval. And it should be somewhat quantitative. And indeed, there is a bound like that, but it is interpolated. So if you choose any number r, which in practice will be very small, then you can bound the total L2 norm of your function in terms of what we really want, which is the bound on the L2 norm on the union of these intervals that we had before. And then this is taken to some power kappa, which turns out to be like e to the minus constant over r. So if r is very small, then kappa is very small too. So you shouldn't take r very small. Why can't you take r very large? Is because the other part isn't the L2 norm of the Fourier transform. It's easy to see that such a bound, just bounding f in terms of f here, wouldn't be really possible. Well, after all, there do exist compactly supported functions. But here you take the Fourier transform, and then you take it with an exponential weight, where r is participating. So there is a certain game here with choosing this r, not too large and not too small. Now, how would you prove a lemma like this? Well, you just use the analytic continuation to the strip of size r. And then log of this analytic continuation of f is a subharmonic function. Log of the absolute value is a subharmonic function. And then you just use the standard bound that comes from the, a function at the point is bounded by the integral of over the harmonic measure. Because we use logs, we will have products and powers here rather than sums. And if we look at what the harmonic measure estimate does, is that the top and the bottom would give you this second term here. And the middle will actually give you the L2 norm on this interval I prime. But you have to take it to a power which is the harmonic measure of this interval. And then if you have a very thin strip, then the harmonic measure, you will only have probability e to the minus c over r to actually reaching with a Brownian motion somewhere far enough to here. So that's why the bound is like that. So that's the bound that we will use. Of course, it says nothing about it. It doesn't use the support property of the Fourier transform. So how would you use the support property? Well, so that's the second part, and that's more difficult to prove than the first one. But luckily, it has it comes from a field that has been very well developed. Namely, imagine that you have a regular set. So you have this fractal set. And it turns out that you can construct a compactly supported function with very small support. So here we take an interval of size c over 2 around 0, where c was the size of this interval. You can take c over 10. It's just, have to allow yourself a bit of room, right? And then this function has a few properties, but the two important properties, well, certainly it's not identically 0. That's important. But what's really important to remember is that it's compactly supported. That's number one. Number two is that psi hat of psi is bounded. So I'll just remove all constants here by x of minus log, and I'll even do it like that, which is somewhat illegal. Absolute value of psi, where psi is in y. So you can get a function which is has nice bounds, independent on this high frequency n that we used. And it has these bounds only on y, but if we look at the bound, what is it? So here we have a power that's strictly less than 1. This 1 plus delta over 2 is, you can choose other numbers there. It just has to be between 1 and delta and sufficiently far away from both. So because this number is strictly less than 1, if you go back to the standard theorem of when you can have compactly supported functions with this decay, you have an if and only if criterion. So this theta would be this power of the log. And then when we do the math, we see that because this power is strictly less than 1, there are no non-trivial, so non-zero, compactly supported functions with this Fourier decay everywhere. So this is an illegal class in some sense. It is a quasi-analytic class. So you cannot have compactly supported functions in it. So obviously, you cannot ensure this for all psi's. And that's where the set y comes in, that you can actually ensure this illegal bound on this fractal set. So this gives you hope. So that's where you would use your fractal set. That you're going to use this psi to jump from to jump into somehow to jump into an disallowed class, and then that will give you these lower bounds. So how does that work briefly? Let's see. I'm afraid there are so many formulas I might have to read the slides. But so how is this psi used? Well, let's take the original function f, whose Fourier transform is supported in this fractal set y. And then let's just take its convolution with psi. So this, why are we taking the convolution? For two reasons. So psi is compactly supported, which means that this convolution didn't completely destroy our ability to get lower bounds on these unions of intervals. The second property is that, of course, the Fourier transform of G is going to be the product of the Fourier transforms. And now we see that our weight psi is small where f hat is supported. So that's how we are able to use the bound on the Fourier transform of this multiplier psi. So well, we want to apply lemma 1 which is this interpolated bound for functions with compact Fourier support. And we want an asymptotic parameter. So what one can do is one can take this function g and split it into low and high frequencies. Oh. Pažoniški poziom energy battery 6%. Wow, that's a bummer. I can continue on the blackboard. It will take me a moment to write it out, but well, I'll while this is being fixed, let me talk a little bit more since time is coming, is going. Oh, great. So it will survive, you think? No. Maybe there could be a charger. All right. Well, we'll see. I might leave you on a cliffhanger. So let's split. Okay. Let me just talk twice as fast, and maybe it'll work. So we replaced our f by its convolution with psi, which has better Fourier decay bound. So we converted Fourier support property into Fourier decay bound, and that's something that's more familiar. Now you split it into frequencies less than some large constant, bigger than some large constant. This large constant will go to infinity at some point. You have to take it large enough to remove the error. So that constant will have to stay with us for some time. I call it k. And then so you just split it. This g1 has frequencies less than k, and g2 has everything else. Of course, because of this Fourier decay, you see that these high frequencies are rather small. So here I just bounded them crudely, but you can do better than that, certainly. And here I will use the h-1 is just the h-1 Sobolev norm on the real line. Now, you apply this interpolated bound to the bounded frequencies, to the frequencies below k. And, well, the question is how to choose this magic parameter r, which dictated the height of the strip or the exponential weight in the Fourier transform. Well, you just choose it to match this decay of psi. So if you choose r, like what is done there, then you will see that this right-hand side, which was 2 slides before, it will still be bounded. So for g1, it will still be bounded in terms of the Fourier transform of f. All right, so that's what we do here. And then we still have this parameter kappa. And that's where we use that this exponent is less than 1, or in other words, we use that we were in this class, which is quasi-analytic, because if you look at this kappa, it is going to decay to 0, but it's going to decay to 0 slower than any power of k. So here I put 1/10, but that's slower than any power of k. So, so what you do then is you want to apply this lemma 1, and because psi expanded the support a little bit, you put some smaller intervals here of half the size of I prime. And then if you want to know this g on one of these I primes, it only depends on f on the corresponding, and this I double prime only depends on f on the corresponding I prime. That's where you use the support property of psi. So then you apply lemma 1 to this g1. So you get this bound that we had before. And what's important is that here you got this norm of g1 on these, say, I double prime intervals. And that one, well, that's actually where the error comes in that you can remove, because your g was a sum of 2 parts. Once you cut off in frequency, you, of course, lost your support property entirely. So you write your g1 as a sum of, or a difference of g and this error. So this one would be this error. And this is really the norm of g on u double prime, which is estimated in terms of what we wanted to begin with. And so you get this. And then you can see that you can plug in this thing into this thing. And then you get a formula here, like this. And what you see here is that was really the bound on the norm of g1, but you can put this error here, so you really get a bound in the norm of g, which is the norm of g hat, which is this. And so you really got an estimate on the L2 norm of f hat near 0, because psi hat of 0 is 1. And then you can shift this, so you can apply this statement to multiplications of f by characters, which do not change the support. And as far as support in the Fourier space, it shifts it, so you just get another delta regular set, which is fine. And so then you can really get an L2 norm of f on the left, and you get this expression. And when you look at this expression, you get something that you really want here, which is the norm of f on the union of intervals. And then you got this error that we produced on one of the previous steps. And so when you look at this error, it would be like k times e to the minus kappa times square root of k. And then once you compute what this is, because we chose our powers correctly here, and this power was less than 1, this error can be removed. So that's a rough technical outline of how the proof would work. So you somehow combine two things here. Well, there is one thing, however, that I did not explain, namely how to prove this lemma 2. So this all relies on the fact that we can find a multiplier that's compactly supported and whose Fourier transform is decaying a bit too fast, but only on this fractal set. So you have to use the fractal nature of y somewhere. The way we use the fractal nature of x is because it had lots of holes in many levels, and we got lower bounds in them. Where do you use the fractal nature of y? Well, you can apply the classical result, which is known as Beurling-Malliavin theorem. So there is no if and only if characterization of how fast you have to decay in Fourier space so that you could still have a compactly supported function there. But the Beurling-Malliavin theorem comes very close. So if you assume that the log of your weight is Lipschitz, then you get an if and only if condition, which is just the integral of the log of the weight with respect to the Poisson kernel is finite. So this is the same as the Ingram's bound that I mentioned before, but this is really, here you don't need any monotonicity property. And that's important for us because we will use this Beurling-Malliavin theorem to construct this compactly supported function with its decay properties on this set, and we will tailor our weight to this set. So the idea here is the following, that the main condition here is really the convergence of this Poisson integral. Now that's an integral condition, and that's good for us because our set y has a lot of holes. So we can hope to find a weight which will be like this only on the set y, and it has to fall off somewhat reasonably so that to not violate the Lipschitz condition, but the integral will still converge. And so that's what you do. So that's rather straightforward to do, in fact. What you can do is you can take your y, and then you can take a partition into dyadic intervals, and each of these dyadic intervals you split into intervals of somewhat smaller size. So L is a dyadic number, and this M is somewhat smaller than L, and it's chosen correctly so that the integral would converge at the end. And then where does the fractal nature of the set come in? Well, you have a big interval of size L. And then you're covering it by intervals of size M, which is much smaller. How many of them actually intersect your set? Well, it's L over M, everything to the power delta. And so you only choose these intervals, and then you just put appropriate weight on these intervals, which looks like that. It's just a head function. You can smoothen it out if you want. And then you just sum them up, and then when you compute the total integral, you see that because we had L over M to the delta and not L over M intervals, the integral will actually converge. So you will get some bound that's independent on the, on N, and you're able to finish the proof of this lemma 2. So I believe I still have 5 minutes left, right? Okay, good. So this finishes the rough outline of how a fractal uncertainty principle like that can be proved. So there is still quite a few slides left. So one can try to prove the Beurling-Malliavin theorem. That's I don't think I'll be able to fit it into 5 minutes. So I should say that the Beurling-Malliavin theorem itself is a rather deep result, and I'm aware of no simple proof of that. Of course, simple is relative, Perhaps to many of you the proof would be simple, but to me it certainly seemed quite difficult. But the reason is because this theorem gives you a very, very sharp condition. So once you have a Lipschitz weight, you really only need this integral to converge. And it's also a necessary condition. The convergence of this integral is well known to be a necessary condition to have a compactly supported function with this Fourier decay. So it turns out that in our case, however, we do not need the full power of the Beurling-Malliavin theorem. And so it's much easier to prove it if you have a bound on the derivative of the Fourier transform of the log of the weight. And it turns out that in this case it's available. So I will skip through the next few slides, but the point in these is that the weight that we have is not the general worst weight than you would need to really exhibit the whole power of Beurling-Malliavin theorem, and so a more, a simpler proof is available here, which uses a Hermann-Dirichlet theorem, extending your weight to an appropriate subharmonic function, and then using the Paley-Wiener theorem to give you what the Fourier transform should be. So I will skip this part because instead I wanted to talk a little bit on the right, and there are a couple of open problems I should also say. That this strategy was very one-dimensional. So this strategy relies on being able to construct a multiplier, so a compactly supported function with given Fourier decay properties, and there is no version of Beurling-Malliavin theorem that would be as sharp in higher dimensions. And in fact, it's worse than that, because the fractal uncertainty principle would actually be false in higher dimensions. If you state it in a naive way, you just consider a horizontal interval and a vertical interval. And you can have a function which lives on a horizontal interval in Fourier space and completely concentrated on a vertical interval in physical space. And it's hard to say why would this principle fail for these very simple sets and suddenly be true for fractal sets. So that's an open problem. And if this problem was resolved in a satisfactory way, then it would give you, for example, these spectral gaps, but for higher dimensional quotients. Now, what I wanted to at least mention is that there are other ways to prove fractal uncertainty principle, or rather a different version of it. So if I go back to this picture, what I described was a fractal uncertainty principle and thus a spectral gap for, with exponent that's strictly bigger than 0, so you get decay, you get some decay, for sets of any dimension all the way up to delta equals 1. Well, not up to, not including, of course. Obviously, for delta equals 1, this statement would be false. Now, Noah's result can be, the techniques of Dolgopyat can actually be adapted using the fractal uncertainty principle, and in any case, they give you that you have an improvement over this basic volume bound all the way up until delta equals 0. So what's the novelty of the result I present here? The novelty is that you get an improvement which only depends on the dimension of your fractal set. And so that's something that's, it's kind of curious, because if you just think about this fractal uncertainty principle, it's not too hard to prove a fractal uncertainty principle for a usual Cantor set, especially if you tailor your constants exactly so that it's, you have 2 pi in your Fourier transform and so on. Then there is a much simpler argument than what I presented to do it. But you can also see that you can construct Cantor sets which would give you points here with very small improvement of fractal uncertainty exponent. Roughly speaking, you just take a Cantor set with a large base and with an alphabet that looks like an arithmetic progression. And so here, however, we claim that there is a fractal uncertainty principle and there is a gap, which I'll just draw it like that. Only depends on the dimension and doesn't depend on, say, the regularity constant of your set. So why is that? Well, we do not claim it for all fractal sets. We only claim it for limit sets of hyperbolic surfaces. And so those look very much like Cantor sets. They can be obtained by a Cantor-like procedure. They are indexed by words in a free group. However, the elements of the group here are nonlinear. So you can use the fact, the worst situation for all of these things, as would be expected, is when your set has a lot of linear structure, a lot of linear symmetry. And here we use nonlinear transformations to generate our set. And so you can use this to show that you will have this better fractal uncertainty principle. And in fact, it gives you something better. It gives you Fourier decay of the associated natural measure. So as we know, if you take, say, the mid-third Cantor set, the Fourier transform of the natural measure there doesn't decay at all. So just being fractal doesn't guarantee Fourier decay. In this case, when you have a nonlinear fractal set, it actually does. So that's another nice statement. And the main tool, which is why I wanted to get to this point, is actually you think of this, of going down this set as applying consecutive transformations. And you can think of it as, if you linearize the problem, as multiplying by a lot of numbers. And because of nonlinearity, the numbers that you multiply by, in the linear Cantor set, they would just be powers of 3. And here they're really spread out. They have a positive box dimension. And then there is an result of Bourgain, which relies on the discretized ring theorems, so on the sum product theorems, that tells you that you have exponential decay. You have decay of exponential sums if you take a lot of IIDs and then you multiply them and then you look at the Fourier transform. And so that's how you can do that. All right, so now I should really finish. Just leave it on this slide. Thank you.